Greetings, fellow students, engineering students. Welcome again to our fourth lesson for Engineering Science N3. My name is Mr. C. Tobejane from Ehlanzeni TVET College, Mlumati campus. And today, our lesson will be looking more into heat. That is chapter 5. If you are using the Future Manager's textbook by Tommy Ferreira. But if you're using another book, I'm not sure about the chapters. They vary, the location of these chapters. But today, we are focusing on heat. Whenever we speak of heat, heat is a form of energy. When there is fire, fire releases heat. We need to understand what exactly happens in these components breaking up to produce this heat. If you are seated next to a heater element, the heater element produces a certain amount of heat. We need to understand exactly what happens in that element, that the combustion that is taking place in that particular element to produce heat. If you are boiling water or cooking food, there is heat transfer from your stove to the pot, from the pot to what? To the water which you are boiling on the food that you are cooking. We need to understand what exactly happens there. Are we having heat loss along the way? Is the amount of heat being produced in that particular heating element equal to the amount of heat which is received by whatever that we're trying to boil out? But first, let us understand the basic concepts of heat. Heat, like I said, heat is a form of energy. If heat is a form of energy, that means it cannot be broken apart and you can't create it. So heat is a form of energy and it's measured in joules. Anything that is energy is measured in joules. Whether you are speaking of kinetic energy, whether you are speaking of potential energy, that is measured in joules. Temperature is an indication of the degree of hotness or coldness of a body. How much a body is cold is measured in degrees. How much a body is hot is measured in degrees. What do we call that? That is temperature. Specific heat capacity is the amount of heat required to raise the temperature of a substance. The amount of heat required to raise the temperature of a what? Of a substance. If I'm heating up water, how much heat should I apply on the water so that the water changes its temperature maybe from 0 degrees Celsius to 1 degree Celsius? That is specific heat capacity. We have a calorific value of fuel, which is the quantity of heat required to completely burn fuel. For an example, you are about to have a braai in your house and you have coal. Coal is a form of fuel. How much heat is applied in those fuel, in that coal, to completely burn it to a point where the coal that you use for braai cannot be reused? That is calorific value. And what is fuel? Fuel is a substance which can be burned in order to release heat energy. But in most cases right now, I want us to focus only on the specific heat capacity concept. We said specific heat capacity is the amount of heat which is produced, or is the amount of heat required to raise the temperature of a substance. On our screen here, we have the equation to calculate more particularly on water or steel. Can be water or steel. Now let me try and emphasize this. Specific heat capacity only works on liquid and steel. It doesn't work on fuels. When it comes to fuel, we use what? Calorific value. But when it comes to liquids like water, we use what? Specific heat capacity. When it comes to raising a temperature of a steel, it can either be an aluminum bar or copper brass, we use specific heat capacity. So we have the equation Q is equal to MC change in T, where your Q, that is the heat energy in joules, M, that is the mass of the substance in kg. C is the specific heat capacity in joules per kg degrees Celsius. And change in T, that is the temperature in degrees or Kelvin. Now, change in T we have T2 minus T1. What is T2? T2 represents the initial temperature, the final temperature of the water. T1 represents the initial temperature of that substance. Suppose this substance has an initial temperature of 15 degrees Celsius. When you burn it, it goes up to a temperature of 25 degrees Celsius. What is the final temperature? 25 degrees Celsius. The initial temperature. So this means that when you have change in T as T2 minus T1, then you are actually increasing. Increasing what? You are increasing temperature. You are increasing temperature. But if you have change in T, which is T1 minus T2, right? You have boiling water. And you have boiling water, you leave the water there to cool down. What are you doing? You are actually reducing temperature. Or maybe you have an iron steel, which has a temperature of 800 degrees Celsius, maybe. And you want to cool this iron steel. You immerse it into water. What are you doing to the iron steel? You are decreasing its temperature. So this is what? Decreasing what? Decreasing temperature. Or rather, heating and cooling in simple terms. You can say heating, and here you can say what? Cooling. Right. I hope you understand that. So, since now we understand these basic concepts, let us see if we can apply them in an example. Let us see if we can apply them in an example. Example 1. Calculate the amount of heat energy required to raise the temperature of a 5 kg of steel from negative 20 degrees Celsius to 140 degrees Celsius if the specific heat capacity is 0.486 kilojoules per kg degrees Celsius. Let us extract our data now. Let us extract our data. Data, what do we have? We have the mass, which is 5 kg. We have the initial temperature, which is negative 20 degrees Celsius. We have the final temperature, which is 140 degrees Celsius. And we also have specific heat capacity, which is 0.486 kilojoules per kg degrees Celsius. You can always multiply this value by 1,000 so that you have what? If you multiply this by 1,000, I believe you're going to have 486 joules per kg degrees Celsius. 0.486 multiplied by 1,000, that is 486 joules per kg degrees Celsius. Now we're ready to calculate. What are they looking for? Q. You see? So equation to use, Q is equal to MC change in T. What is M? 5. Specific heat capacity, 486. Change in temperature, it will be T2, which is 140. Let me put a square bracket here because we have a negative sign. 140 minus negative 20 degrees Celsius. Negative 20 degrees Celsius. We can punch that in our calculators and see what we have. 5 multiplied by 486 into 140. This, mathematically, when you multiply a negative with a negative, what you get? Positive. But if you don't know that, you can simply punch the values as it is. But remember the brackets. So it will be plus 20 or negative minus negative 20. So you must have two brackets closing that up. So the value that you obtain here, it will be 388,800. You divide that by 1,000. If you divide that by 1,000, you're going to get 388 kilojoules. 388 kilojoules. Simple. This is how you do it. Very simple, very straightforward. Now, let us do the next one quickly. Determine the specific heat capacity of a certain piece of metal which has a mass of 20 kg. It was found by experiment that after the piece of metal received 1.8 megajoules of heat energy, its temperature rose by. Right, the temperature rose by 230 degrees. Let us write our data here. Let me just do this and have my data here. We have, what do we have here? We have mass. The mass is 20 kg. Your mass at all times, it must be in kgs. You don't deal with mass in grams. Note, when you have your mass in grams, you must divide that mass by 1,000 so that you can have it in kg. You always deal with kgs, not grams. So this piece of metal, we need the specific capacity of this piece of metal. They say we must calculate C, the specific capacity, if the mass underwent an energy of 1.8 megajoules. What is this now? It means that our Q is given as 1.85 megajoules, which is a very big number, which is a very huge number. You need to know your convections. Unfortunately, in these lessons, we are not going to learn about convections, but you need to know your convections, how to convert kilos, how to convert hundreds to kilos, to millions, to billions, to trillions. You need to learn those so that you can apply it here. Now, they say the specific, we need to calculate the specific capacity. If the temperature rose by 230 degrees Celsius, right? If they say the temperature rose by, this means that they are saying your temperature rose by 230 degrees Celsius from this to that. Unfortunately, we don't have T1 and T2, but we know that the difference between the two is 230. It has risen by. Equation, MC, change in T. What are you looking for? C. Q, M, change in T. Can we substitute? 1.85 exponent mega 6, which is 20 multiplied by 230. Now, let us punch that in our calculators and see what we have. 1.85 exponent positive 6, because it's mega means million. 20 times 230. The value that we obtain here, the specific capacity of this object is 402.17 joules per kg degrees Celsius. Do not forget the SI units. SI units, they're very much important. Was there anything which is difficult? Nothing. Nothing is difficult at all. Moving right along. Now, let us talk about heat transfer. Let us talk about heat transfer. With heat transfer, we know and we understand that heat can be transferred from one object to the next object, right? There are certain laws and certain principles that you follow whenever you're dealing with heat transfer. So it means that even yourself, heat can be transferred to you. You are feeling cold and you sit next to a fire. Heat is transferred to you. Then that makes you feel warm. If maybe, for an example, you are cooking, take your pot, put water and put it in a stove. What happens? The heat produced by the element of that stove will be transferred where? To the pot, transferred to the water. So there's a certain principle along that transfer which we need to follow, which is the principle of conservation of energy. What does it state? The principle of conservation of energy states that energy cannot be created or be destroyed, but can be changed or transferred from one form of energy to another form of energy, right? It can be changed from one form to another or be transferred from here to there. Other practical example is the light. The light, they use the principle of energy because it is transferred, or rather, it is converted from electrical energy, right, to light energy. Your speaker converts electrical energy to what? To sound energy. Do you understand? So this is basically the transfer of energy itself. This states that you cannot create energy and you cannot destroy energy, but you can transfer it from one form to another form. We have an example here, example 2. Example 2 says, after a steel component was welded, its temperature had risen to 850 degrees Celsius. It was quenched in a tank containing 30 liters of water with an initial temperature of 19.5 degrees Celsius until both the component and the water reach an equal temperature of 25 degrees Celsius. Now, I want to emphasize something here. If I take a steel component having a very high temperature and I want to what? I want to decrease, I want to cool the component down, and I immerse it in water. What happens is that the steel component will transfer heat from it to where? To the water, right? Heat transfer will take place. It means that this component will cool down, but what happens to the water? The water will increase in temperature, right? That's just simple logic. You can't have the same temperature from when you have immersed the water being equal, the steel being equal to the temperature of the water initially, right? So this steel component was welded, and after it was welded, it reached a temperature of 850 degrees Celsius. Now we want to cool down this steel component. We quench it in a tank containing 30 liters of water. The water had an initial temperature of 19.5 degrees Celsius. Now, after I've immersed it, both the component and the water, what happens? They both now have the same temperature. Data. It's very much important to extract your data. Extracting your data always assists you in determining how much of the information you have, which equation to use, how to use it, and when to use it. Steel component was welded and the temperature risen to 850, so we have we have T1 of 850 degrees Celsius. 850 degrees Celsius. How do I know that this is T1? It's because along the statement they told me that both the component and the water reached an equal temperature of 25 degrees Celsius, which means the water had 25 degrees Celsius and the steel had 25 degrees Celsius finally. So that is T2. That is T2, 25 degrees Celsius. Let me just separate this. This is for the steel. The steel, sorry, not steel. And then what? The water. T2 of steel, T1 of steel. What else do we have on the steel? They say assuming that no heat was lost and that the specific heat capacity of the steel, that's what we are looking for. The specific heat capacity of the steel is 494 joules per kg degrees Celsius. You see, we have everything for the steel. What is it that we're not given of the steel? We don't have the mass of the steel. Can you see that? We don't have the mass of the steel. But let's look at the water. Water had an initial temperature of 19.5 degrees Celsius and a final temperature of 25 degrees Celsius. They said here the water has a mass of 30 liters. 1 kg is equal to 1 liter. So M 30 kg. We can write it like that. We also have the specific capacity of water. Specific capacity of water, 4,200. It's 4,200 joules per kg degrees Celsius. What happened here? The steel component transferred heat to the water, right? So now the question says calculate the mass of the steel component. Here's what we do. Q of steel, which is lost or transferred, is equal to Q of water, which is what? Gained. Right? Water gained heat, steel lost heat. We know that Q is equal to what? MC change in T, right? MC change in T. So we can say MW, CW change in T, W for water, MS, S for steel. What are we looking for? The mass of the steel component. We divide both sides by C change in T. So we're going to have MS is equal to MW, CW change in TW divided by CS change in TS. Then we put in our values here. We substitute our values here. The mass of water, 20. Specific capacity, 4,200. The change in temperature will be 25 minus 19.5. Divided by specific capacity of steel, which is 494, change in temperature, 850 minus 25. Let us punch that in our calculators. Let us punch that in our calculators. Put that in our calculators. We have 20 multiplied by 4,200 multiplied by 25 minus 19.5, all divided by 494 multiplied by 850 subtracting 85. And the mass of the object is found to be 1.13 kg. Very simple. What is it that you need to know? You need to be able to understand what is it that you are given, where to use it, how to use it, and why are you using it in that specific area. Again, understand your equations. The more you understand your equations, the more this becomes simple. You won't need to spend too much time in an exam room going through your formula sheets and so forth. Just practice your equations, know them, so that when a question comes, you simply know which equation to apply, than wasting too much time in an exam center. Let us make one last example, since we still do have a little more time. Example 3. Now this is a very tricky one, because you don't only deal with just 2 components, but you are dealing with 3 components. It means that there's one component that's transferring heat to 2 components. A piece of aluminum with a mass of 40 grams is heated to 200 degrees Celsius and then cooled in a 160 milliliters of water, which is contained in a copper vessel weighing 24 grams. The initial temperature of the water and the vessel is 12 degrees Celsius, and the specific capacity of water is 4.19 kilojoules per kg degrees Celsius. Assume the specific capacity of the copper to be 390 joules per kg degrees Celsius and no heat was lost, or no heat loss occurred. If the final temperature of the water is measured and found to be 28.8 degrees Celsius, determine the specific capacity of aluminum. Now, I may advise you, if you are attempting such a question in an exam room, you don't have to read out the whole question before answering it. Just read piece by piece, extract your data piece by piece. It will then simplify this whole history book. But let's try and unpack this now. Let us try and unpack this. I'm at war now. This chalkboard, this whiteboard is fighting me. It's fighting back. Right. Quickly, they said a piece of aluminum. So what we have? We have aluminum, we have water, and then we have a copper vessel. We have the vessel. We have aluminum, we have water, and we have the vessel. They say the aluminum has a mass of 40 grams. A mass of 40 grams. I said that you don't deal with mass in grams. You need to convert that. We'll convert that in a later stage. That aluminum is heated to 200 degrees Celsius. 200 degrees Celsius, and then cooled in a 160 milliliter of water. That is the mass of water, 160 milliliters. We still need to convert that to kgs. We'll look at that. For now, let's extract our data, which is contained in a copper vessel weighing. The mass of the vessel is 24 grams. The initial temperature of the water in the vessel was 12 degrees. So T1 of this is 12 degrees Celsius. T1 of that is 12 degrees Celsius, and the specific capacity of the water. So we are given 4.19 kilojoules per kg degrees Celsius, but I always prefer to change that to be in joules per kg degrees Celsius. So C will be 4,190 joules per kg degrees Celsius. We did the conversions. You know how to go about doing that. Right, and then they say here, assume the specific capacity of the copper. Where is our copper? That is our vessel. Has a specific capacity of 390 joules per kg degrees Celsius, and no heat losses occurred. The final temperature of the water is measured and found to be 21.8. Now, if the final temperature of water is measured and found to be 21.8, we have the aluminum immersed inside the water. The water is contained in a copper vessel. This means that if the final temperature of the water after this aluminum is cooled down is 21.8, that simply means even the copper vessel has a final temperature of 21.8, even the aluminum has a final temperature of 21.8. So 21.8 degrees Celsius, 21.8 degrees Celsius, 0.8 degrees Celsius. Let us convert this, that, and that to kg. 40, when you convert it, we did it, I explained to you. You know how to go about doing it. 0.04 kg. The milliliters of water, we know that milli is actually exponent -3. So we have 160 exponent -3. We need to change it to kg. So we divide this whole thing by 1,000. Then we know this will be 0.00016 kg. And then our 24 should be 0.024 kg. Right, now let us quickly calculate. There's heat transfer, we are wrapping up. So we have Q of aluminum, which is losing. Q of aluminum is giving to who? Is giving to Q of water and Q of vessel, right? We know that this is MC change in T of aluminum. This is MC change in T of water. And this is MC change in T of vessel. What are we looking for? The question says, determine the specific heat capacity of aluminum. CA, that is what we are looking for, right? So you divide everything by this. So it means we're going to have C is equal to MW CW change in TW plus MV CV change in TV divided by what? Divided by MA change in A, like that. So from here, substitute your values. You have your mass, you have your specific capacity of water, and then you have to obtain your answer there. Now, because of time, I'm going to leave that to you to do your calculations, and if you get it, just you write it. You write for on our Facebook page. You can post a post there so that someone can find it, or you can follow up the conclusion of this, how we go about putting up the values there. You can see it on our YouTube channel, Ehlanzeni TVET College, or you can even check it on our website, ehlanzenicollege.co.za, or find us at Twitter at Ehlanzeni TVET College. But that's it for me, and we are going to meet next time.